So we are 2 weeks done with the summer semester. In the third week, we will take our first exam. We don't know what day of the week it will be on. He didn't tell us. He'll probably decide at the last minute, all right, we're doing it tomorrow. So so we'll take the test. It's going to be one theorem plus 2 homework problems. Although the goal is to get up to 12 problems solved. Or not 12 problems, 12 points total. If you don't know how the point system works, look at the last video. But my goal was to do the theorem and then do 2 like middle problems, like medium difficulty problems, and get the 12 points that way. And usually he does not tell us or give us like any hint as to like what the theorem is going to be. The way he teaches, like he gives you incredibly dense set of notes and he expects you to memorize all of it. Although he wouldn't use the word memorize, he would use the word learn. But if you give me 2 weeks, then memorization is all I can give you, unless the theorem is pretty simple. But in an unprecedented move, he did give us a list. So this is a first for him. He's given us a list of potential theorems that he will put on the exam. And he's labeled them as questions here, but they're really just theorems. So he'll pick something from this list, and then we're expected to prove it. So that's basically what I'm going to do this weekend. I'm going to review all these theorems, try and prove them, or at least understand them from my notes. And the first 4, actually he hasn't even talked about 7 and 8 yet. I think he's behind. And I think he kind of alluded to 6. I can't really remember if he proved 6 or not. But 7 and 8 he hasn't done. And some of these, the earlier ones, are a bit harder to, they're involved to prove, like finite dimensional Hahn-Banach theorem. Whereas other ones aren't too bad, like rank nullity theorem's easy. Cauchy-Schwarz inequality is easy. In fact, the Cauchy-Schwarz inequality is going to be the subject of today's video, which is why I have it on my marker board up there. Cauchy-Schwarz inequality is like that inequality. It shows up all the time. Applied mathematicians use it. Pure mathematicians use it as well. I asked him in class if it was his favorite inequality because of how much he talks about it. And he said it's everyone's favorite inequality. And at one point they were trying to show if every inequality follows from it, whatever he meant by that. So, and it's depending on what field of math you're in, it'll take slightly different forms. So we're going to be looking at this form up here from vector spaces because we're in linear algebra. Linear algebra, before we get really into the proof, it's one of those subjects that I think you should, if you don't really like math but you haven't seen linear algebra yet, look into a linear algebra course. Like look at what type of subjects they're doing and see what they do. Because a lot of people, like even that aren't in the math field, like I had a computer science instructor a long time ago. We were talking about math at one point because I told him I was a math major. And he said that he had like some math subjects he really liked, others he didn't really care so much. But when he took linear algebra for the first time, he's like, he fell in love with it because it's such an interesting course. It does kind of feel natural to me more than some other mathematics because, as I've said on the channel, I was a math major. It got hard, so I switched to environmental science. And then when I graduated, I went back into math and I took that one math class in spring semester 2018 as a non-degree student. And I had to pay out of pocket, so because of that, I only took one class. And it was Advanced Linear Algebra with the Sheldon Axler book, Linear Algebra Done Right. And I think back to that class a lot because that was kind of like, it was a class that was sort of getting my feet wet back into math to see if I could really do it. Like, because it was a tough class for me at the time. There's a lot of proofs involved, a lot of tricks. I remember there were homework problems that had really involved tricks in it that I've never seen before. And they were like, you should expect, just like, what, you don't know Euler's equation? Like e to the I theta equals cosine theta plus I sine theta? And like my teacher like expected me to know that already. I was like, I've never seen this before. I'm from environmental science. So it was a tall order back then, but looking back now, that book that he used for that class was really good. I really liked that book. I really liked the way he did linear algebra in the book because everything just made sense. I read the book with ease. And when you're studying mathematics and you want to do research and you're reading papers all the time, you really start to appreciate people who can write, or at least people, maybe he's just writing in a way that's really easy for me to read, maybe not so much anyone else, but I think it's more so the former. I think he's just, the authors, you really appreciate a good author, someone that can explain something in plain, simple English. So that's what I'm going to try and do with the Cauchy-Schwarz inequality. So let's look at the statement, but before that, I want to look over some definitions first because we need them for what we're about to say in case you're not familiar with it. So the idea is that you have this vector space X. And when we have a vector space X, it's usually defined over some field, which is where our scalars come from. So in this case, we're considering the field of complex numbers. So the idea is that we want to define this function over the Cartesian product x cross x. And this function is denoted with the brackets and the two dots inside. It's a function. It looks kind of weird because usually we like to denote a function with like f or something. But it makes sense to write it this way because you take two inputs like v and w, like down here. You compute something and you'll get a complex number in the end. So this function is called a scalar product if it satisfies these conditions. So the first condition is that if you take any vector and you take its scalar product with itself, you're always going to get a non-negative real number. So even though we're over the field of complex numbers, this number could very well be complex. But for any vector v, if you take its scalar product with itself, you're going to get non-negative real. Okay. And then I have this other one. I call it 1.5, but really, I really call it that because this is kind of associated with the first one, so they may just label it this way. But what it says is that if the scalar product of a vector with itself is 0, this is true if and only if the vector v is 0 itself. So no other vector outside of 0, if you take its scalar product with itself, is 0. Okay. The second property says that if you take a scalar product of v and w, then this is equal to the scalar product of, w with v, but then you must take the conjugate of it. So the conjugate just means if you have a complex number, a plus bi, the conjugate is going to be a minus bi. You flip the sign. So remember, we're over the field of complex. Our output is complex numbers. And then the third property is called linearity, which says that in the first position, you have alpha v plus beta w, where v and w are vectors, and alpha and beta are complex numbers, which is this c. If you take the scalar product of this guy with some other vector u, whatever it is, then you kind of have like a distributive property type thing going here, where you can split this scalar product into two scalar products, where you have scalar product plus scalar product with alpha v and u and beta w and u. But then that scalar that you have here, alpha and beta, can be pulled out. So I can pull the alpha out of v, I can pull the beta out of w, and this is what I end up at the very end. So that's the linearity property. And you might ask the question, okay, so what happens in the second position? Like, let's say, you have u in the first position and you have this linear combination in the second. And the idea is that, you can split it up over, the addition. You can have scalar product plus scalar product. And then the idea is that we want to be able to pull out alpha and beta. But it's not just alpha and beta that you pull out. When you're over the field of complex numbers, we actually have to have alpha conjugate times that inner product and beta conjugate times that scalar product. So when you're in the second position in the scalar product, you have to include these conjugates. And the reason why this is not listed up here is because you can actually show this from this. And the conjugate comes from applying the second one. It's a good exercise to do yourself. It's not hard at all. So that is what a scalar product is. And you probably heard me say earlier inner product here. There's a couple different names for it. Scalar product, inner product, dot product is another one. Textbooks will pick their favorite and do that. So the one that we're looking at, the terminology we're using here is scalar product. Okay, so some basic examples that we see all the time. Let's say that our vector space is Cn. So x and y are two vectors. We can denote them as an n-tuple, where each of these terms are complex numbers. And the field that we're taking our scalars from is the complex number field. The most natural inner product that we have seen that, is like the very first one that you ever see. In fact, they'll just call this the scalar product and not even bother with this guy up here. Is when you take terms in the n-tuple and multiply them together, but we take the second term and we conjugate. So we have to take the conjugate of each of one of these guys to get this. And to simplify, we can write this as a summation, xk, yk bar. So that's the basic one we see. And you can see that if we're looking at Rn over R, then the conjugate doesn't really play a role here, because the conjugate of a real number is itself, in which case you'll just have summation xk, yk. That's Rn over. In fact, I was going to just do that, but then I was like, no, let's stay in complex. Let's stay in the complex field here, because I want to use these conjugate properties. Okay, so that's one example, but there are other examples of scalar products. Like, let's say that you're looking at a vector space of polynomials up to degree n. So the idea is that we are looking at polynomials of the following form, where ak is a complex number, ak is our scalar, xk is that variable in the polynomial. And this is a vector space, and we can endow it with a scalar product defined here. So if I have two polynomials f and g, I can define their scalar product as integral from 0 to 1, f times g bar, integrate with respect to x. And when I first saw this, I was like, okay, it looks weird. And then but you can go through the properties and verify that it's a scalar product and all that good stuff. But something I wish people had pointed out was the similarities between this guy and this guy, because integration is like the continuous form of the summation, which is like the discrete form of this. And you can think of fx as playing the role of xk, and gx as playing the role of yk. Remember, f is a function. You give it x, it returns some other number. And here, you can think of xk as a function of k, where you give it that index k and it returns xk. It's a little bit confusing because x here is not the same as x here, but you can appreciate the similarities between these two. So I thought I would mention it here. Go through your textbook if you've seen these guys before, because your textbook will probably explain it better than I do. Okay, so now we're ready to look closer at the Cauchy-Schwarz inequality. So what exactly does it say? You have two vectors v and w, and you can make the following statement, that if you take the scalar product of v with w, take the absolute value of it, square it, then that is going to be bounded above by the scalar product of v with itself times the scalar product of w with itself. And that should make sense, because yes, these guys are complex numbers on the right-hand side, and this is a real number, specifically a non-negative real number. But remember, this is actually non-negative, and this is non-negative because of the first property. So it makes sense here, this inequality. Okay, so the proof of it is not that difficult, but it feels a little bit long if you want to go through it thoroughly. Once you go through it a few times, you'll be like, oh, this is no big deal. So the first thing I want to do in the proof is show that if one of the vectors is 0, then you'll get like 0 less than equal to 0 up here. And the first thing I do is I denote v with the double bars as the square root of the inner product of v with itself. And the reason that is because if I have some sort of scalar product, I can use it to define a norm. So a lot of times you'll see me refer to this as a norm. But this is how I'm going to denote it because it's convenient for me. So my first claim is that you will actually have equality up here if and only if the set of vectors v and w is a linearly dependent set, which means if you set the linear combination to 0, that means that all coefficients, there exists at least one coefficient that's not 0 that satisfies that equation. So I said that very weirdly, so let me say it again. In fact, it's easier to do it via the definition of linear independence. So a set of vectors is linearly independent if if I take any linear combination, set it equal to 0 of those vectors. That is only 0 if and only if all coefficients are 0. And linearly dependent means that it's not linearly independent. It's kind of a mouthful, but that's essentially what this is saying. Okay, so let's assume for the time being that V and W form a linearly dependent set. So we're going in this direction. So we assume this is linearly dependent. That means I can find a scalar C where V is equal to CW. Obviously, that's more or less the definition of another equivalent definition of linear dependence. So we can actually compute it. So let's look at the absolute value of V and W. What can we do here? Well, because of this, we can substitute in CW for V, which gives us this. But then we can pull that C out from one of the properties of scalar product. You can pull it out and put it here, which is what I have. But you have absolute value of a number times a number. So I can write that as absolute value of C times scalar product of W with itself. Remember, this is non-negative. But what is this? This is just this guy with W instead, squared. So this guy can be rewritten this way. And then just to emphasize that norm W squared is norm times norm, I've written it here. And the only reason I've written it that way is because I want to emphasize that you can actually push this C back inside the norm. And that's exactly what I do here. But what is the norm of CW? CW is equal to V. So this guy becomes the norm of V times the norm of W. And this is essentially what we wanted to show for the equality case, more or less. Because if I take if I square both sides, then this guy is squared. But if I square this guy, these square roots will disappear. And you'll end up with this guy, but with equality in its stead. And then the argument for W as a linear, a scaled copy of V, so W is equal to C prime V for some other scalar C prime. You get a similar computation where you swap the role of V and W, or you swap them here and here. When you take the conjugate, it doesn't affect the modulus. So this guy ends up becoming this guy from the similar computation that was up here. So that's nice. Now, suppose that V or W is equal to 0. For the sake of argument, let's say V is 0. Well, then you can just take the scalar C to be 0 itself, so 0 times W is 0, in which case you'll have a linearly dependent set. Apply this argument up here, and you can show that you have equality in the end, in the case where V is equal to 0. If W is equal to 0, you get a similar argument. So you do get equality if one of the vectors is 0. So this takes care of the case where one of the vectors is 0. Okay. So really, the interesting part is, and yes, I am aware that we did this direction, but we didn't do this yet. But by the end of the proof, we'll have the other direction. So it gets a little bit postponed. So for this argument now, we want to consider what happens if we have a non-zero vector. So assume that V is a vector in X and it's not 0. This is the interesting case, quote unquote. What we're going to do, I've been watching too many stupid YouTube videos, people saying, what are we going to do? If we're going to define a vector Z to be W minus this creative scalar that I've defined here times V. Remember, this is just a number. This is a number, this is a number, number divided by number is still a number. And it's not really obvious, like, where's this thing coming from, because it kind of just falls out of the sky. But really, the definition of Z is motivated by what we're going to do next, because what we want to do is define a vector Z that is perpendicular, essentially, to V. The real word I should use is orthogonal, which is just a generalized notion of perpendicular. Okay, so the idea is this. We take the scalar product of Z with W. We know what Z is in terms of V and W, so we substitute it in here. And then you can apply the property, the linearity property of scalar product to expand and get this. But what happens here now is that this scalar product will cancel with this scalar product in the denominator, and then you'll have WV minus WV, which gives you 0. So by construction, we've made a vector Z that is orthogonal to W, or to V, that is. And usually the symbol that we use to denote perpendicular or orthogonal is this upside down T shape. So visually, what are we doing here? So one way that we can visualize it is to think about it in the space Rn, where you have some vector V. It points in some direction from the origin. And then we can consider the plane that is orthogonal to V, which is usually how I denote it as V perp. I denote it that way because I see other people denote it this way. So V perp is the plane that's perpendicular to V. And W is this vector that's out here somewhere. Remember, V and W are given to us in the very beginning. And this vector Z that we have built here is the projection of W onto the plane V perp, essentially. So that where is Z in terms of our plane? It's this guy that's right down here. And what this does, as you can see here, is I've drawn a right triangle. And what we want to do is apply the Pythagorean theorem to W, because the length of our vector W gives us our hypotenuse, and then we can compute these legs as follows. So that's what we want to do, apply the Pythagorean theorem. Okay, so Pythagorean theorem, right? A squared plus B squared equals C squared. So our C is the norm of W. It's just the length of this vector. Our A or B, whichever you want to call it, is going to be norm of Z. So it's this side of our right triangle. And then what is this? Well, this is going to be the scalar product of W and V over the scalar product of V with itself, quantity squared, times norm V squared. Another way of saying it is what happens if you take W and project it onto the span of V, and you want to look at how long that vector is. So that's how we're getting this value here. Whew. Okay. So just do basic algebra now. Just square everything. We can rewrite this guy as norm V squared. So I have norm V squared squared, which is what I've written here. And then this guy will cancel with one of these guys downstairs. And if we reduce that, we'll get the following expression. We have scalar WV squared divided by norm V squared plus norm Z squared. But this is a non-negative term, this Z. So if I remove it, I'll get something smaller. So if I remove it, I'll just be left over with this guy that's right here. And then what do we have? We have the norm of W squared is bigger than or equal to this guy. And now it's obvious what you want to do to finish. Just multiply both sides by norm V squared. So doing that, we have this, and then we make the observation that the norm of V squared and the norm of W squared, where's my other sheet of paper, is like squaring this guy. So square it, square root cancels with square. Boom. You have the Cauchy-Schwarz inequality. But we're not exactly done yet, right? Because I haven't proven the full implication that's shown up in the claim here. So if you assume that you have equality, so let's assume that you have this statement here. Well, if you have this statement, what can you say about the norm of Z squared? It has to be equal to 0, right? It has to be equal to 0 because of what we wrote down here. You know, this is only, the bottom line is only has equality if the norm of Z squared is 0. But because of the way we've defined a scalar product, one of the properties says that if this is true, that means Z has to be 0. So if Z is 0, that means the way we've defined Z means that these two terms have to be the same, which means this, which means W is equal to some scalar times V. And that's the definition, more or less, of linear dependence. So you have a linearly dependent set, and the reverse implication is shown. And that's Cauchy-Schwarz in terms of vector spaces, more or less, using that Pythagorean theorem. We actually did it kind of differently in class. We used the proof that involves the quadratic, analyzing a quadratic. But I like the one with the Pythagorean theorem more, although he may get agitated at me if I do it a different way. I don't know. He may require other things in that proof that I looked up just now to do this guy. But if Pythagorean theorem is given to me and I can use it for free for vector spaces, then by all means I'm going to do it, because I prefer 5th grade geometry as opposed to 8th grade quadratic formulas, I guess. Anyway, so before I finish this video, I do want to mention the measure theory series of videos. I know this was a big video, it's almost 30 minutes, but one more thing. The measure theory review series is being done right now. I've recorded 12 videos so far. I don't know how I want to post them to the channel. I don't want to do them in like one big dump, or I might do them like in pieces, like I'll upload like 5 and then another 5 and then another 5. Or I may do them one at a time. I'm not sure how I want to do it. But I've recorded about 12 so far. I'm going to record more today, and hopefully it will get done on time. That is my goal. And so far it's been pretty good, although I do kind of wish I was doing some things differently, but that's a topic for a later discussion. Anyway, thanks for watching.